Assalamualaikum and hi everyone. Today we are going to learn on how to perform calculation involving Bohr's atomic model. Here is the formula used for the next calculation. So there are 6 formulas that you have to remember. So we take a look at the question. One of the lines in the atomic hydrogen line emission spectrum falls in the visible light region and has a wavelength of 410.2 nanometer. So first question, give the name for this spectrum series. Okay, next, determine the transition of the electron involved. Calculate the energy of the electron at the excited level. Calculate the energy emitted as a result of the transition. Determine the frequency of this transition. Calculate how much more energy in kilojoule per mole is needed to ionize the hydrogen atom. Okay, for the first question A, give the name for this spectrum series. So, as already mentioned in the question, so the clue for this question is visible light region. So you have to remember all the 5 series. So here I will share to you the easiest way to memorize all the 5 spectrum series. Right? So we can use mnemonic to memorize all the 5 series. So just remember. Okay, for series lime, pasta, bread, fun. Okay, Li is stand for lemon, me is stand for Balmer, pasta means passion, bread means bracket, and fun for fun series. Okay, and then you have to remember also the ground state. Lemon is n equals to 1, Balmer n is equals to 2, passion n equals to 3, bracket n equals to 4, and fun is n equals to 5. Okay, the next is you have to remember also the spectrum region. Okay, lemon is in UV or ultraviolet region. Balmer is in visible light region. As for passion, bracket, and fun is in infrared region. So just remember UV, V, 3IR for the region. Okay, as for this question, the answer here is Balmer series. Okay, for the second question, determine the transition of the electron involved. Right, so in the question only given to you the wavelength that is 410.2 nanometer, and we already known that the series is Balmer series, which the ground state is n equals to 2. So we can use this formula, but remember the values of RH, Rybert constant, we have to choose this. 1.097 times 10 power of 7 per meter, since we want to calculate the wavelength. Okay, so unit for wavelength should be meter. Okay, right, next, second thing that you have to remember is about the N1 and N2. N1 should be smaller than N2, so that the value of wavelength must be positive value. Right, so since we know that the ground state is n equals to 2, but we don't know what is the excited state. So we have the idea that the ground state should be smaller n than the excited state. So therefore n1 is equals to 2, n2 is what we want to find out, which refer to the excited state. Okay. Okay, for the next step, so we can substitute all the values, but remember, so we have to convert the wavelength from nanometer to meter. Since the value of Rybert constant, the unit is in per meter. Okay, right, so how that we can convert from nanometer to meter? So just time 10 power of negative 9. Okay, whereas to convert from meter to nanometer, so you have to time by 10 power of 9. Alright, so convert the unit for the wavelength nanometer into meter, and then substitute the value of RH. So from here we notice that we can cancel out the unit of meter and per meter. Okay, next substitute the N1 which refer to 2, and N2 we can substitute or represent it as X. Okay, and from here, so we can find out the value is 36. 1 over X squared equal to 36. So X is 6. So means we have to the answer here, you have to calculate 1 over 36 and then square root. Then you get 6. So the answer back the question. So the electron moves from N equals to 6 to N equals to 2. Okay, for question C, calculate the energy of the electron at the excited level. So from the previous calculation, we already find out the excited level or excited state for the electron is N equal to 6. So we want to calculate the energy of electron at N equal to 6. So therefore, we can use this formula, En equals to negative RH times 1 over N squared, where N here is referred to 6. Okay, substitute all the values and we will find out the energy of electron at the excited level is negative 6.056 times 10 power of negative 20 joule. For question D, calculate the energy emitted as a result of the transition. So energy emitted here means energy difference. So there are two formula that you can use. Either delta E equals to Hc over lambda, or you can use delta E equals to RH times 1 over N initial squared minus 1 over N final squared. Alright, so for my suggestion, it's better if you use formula number 6 here. Since in the question is given the information about the wavelength. Okay, alright, so if you use the formula number 3 here, so you will substitute the value of N initial and N final, which you already calculate from the previous calculation. So try to avoid to substitute any value from the previous calculation, because we don't know whether the value that we calculate in the previous calculation is correct or not. So please choose this formula. Okay, formula number 6. Okay, next write the formula that we are going to use. Delta E equals to Hc over lambda. Alright, don't forget to convert the unit of wavelength, okay, from nanometer to meter. Then substitute all the values. So from here, we notice that we can cancel out the unit of per second with per second, meter, cancel out with meter. Okay, and then finally, the delta E is 4.84 times 10 power of negative 19 joule. And remember one more thing, rewrite it again in form of sentence. Energy emitted is 4.84 times 10 power of negative 19 joule for the conclusion. For question E, determine the frequency of this transition. There are two formula that you can use, whether formula 5 V or frequency is equal to C over wavelength, or formula number 4 delta E equals to HV. Right, so my suggestion is better you use formula number 5, because if you use formula number 4, you are going to substitute the values of delta E from the previous calculation, which we don't know whether the value of delta E in the previous calculation is correct or not. So there is a high risk, very high risk. So better use formula number 5, substitute all the values. Remember, the wavelength should be in meter, okay, since the unit for speed of light is meter. So from here we can cancel out the unit of meter. And finally, the frequency for this transition is 7.314 times 10 power of 14 per second. Okay, so another unit for per second, so you also can write, okay, hertz, hertz, Hz, hertz, For the last question, calculate how much more energy in kilojoule per mole is needed to ionize the hydrogen atom. So we already know that the ground state for Balmer series is N equals to 2. So you can use this formula where Nr is equals to 2 and N final is equal to infinity. So why infinity? Because question asks to ionize hydrogen atom, means hydrogen become ion and release electron. Electron become free electron and it is located at N equal to infinity. Right, substitute all the values. Remember, please choose RH value 2.18 times 10 power of negative 18 joule. Okay, and we will find out the value of delta E is equal to 5.45 times 10 power of negative 19 joule, which refer to energy needed for one single tiny electron. But in the question here asked in unit of kilojoule per mole, therefore you have to extend for the second step calculation. Okay, for the second step calculation, so we know that previous calculation we already calculate for one energy for one electron. Okay, now the unit is in per mole, which refer to 1 mole electron. So we can write like this: 1 electron is equivalent to 5.45 times 10 power of negative 19 joule. And we know that in 1 mole of electron contain 6.02 times 10 power of 23 electrons. So we want to find out how much energy needed for 1 mole electron. So you just substitute all the values here and we will get the values of energy is 328,090 joule. Okay. Now we want to convert into kilojoule. So time 10 power of negative 3 or divide by 1000. And finally, the energy needed is 328.09 kilojoule per mole. Okay, that's all for today. Until we meet again in the next class. Bye.